Hello everyone. My name is Dr. Raj Dandekar. I graduated with a PhD in machine learning from MIT in 2022 and I am the creator of the Build DeepSeek from Scratch series. Before we get started, I want to introduce all of you to our sponsor and our partner for this series, Invideo AI. All of you know how much we value foundational content, building AI models from the nuts and bolts. InVideo AI follows a very similar principle and philosophy to that of us. Let me show you how. So here's the website of InVideo AI. With a small engineering team, they have built an incredible product in which you can create high quality AI videos from just text prompts. So as you can see here, I've mentioned a text prompt, create a hyper realistic video commercial of a premium luxury watch and make it cinematic. With that, I click on generate a video. Within some time, I am presented with this incredible video, which is highly realistic. What fascinates me about this video is its attention to detail. Look at this. The quality and the texture is just incredible. And all of this has been created from a single text prompt. That's the power of NVIDIA's product. The backbone behind the awesome video which you just saw is NVIDIA AI's video creation pipeline, in which they are rethinking video generation and editing from the first principles. To experiment and tinker with foundational models, they have one of the largest clusters of H100s and H200s in India and are also experimenting with B200s. Invideo AI is the fastest growing AI startup in India, building for the world. And that's why I resonate with them so much. The good news is that they have multiple job openings at the moment. You can join their amazing team. I am posting more details in the description below. Hello, everyone, and welcome to this lecture in the Build DeepSeek from Scratch series. In the previous lecture, in the previous series of lectures, we have covered extensively the major innovation of DeepSeek, and that is MLA or multi head latent attention. When DeepSeek introduced latent attention, they got the best of both worlds. They reduced the KV cache size and at the same time maintained language performance. And that was just beautiful to see. But along with latent attention, one of the other major innovations which DeepSeek made was something which is called as mixture of experts. And we are going to look at the main idea of mixture of experts in today's lecture. In the subsequent lectures, we will get started with the mathematics of mixtures of experts, and then we'll see exactly what's the new thing which DeepSeek did. Now, one thing to note is that mixture of experts as an idea has been around for a very long time. And when I say very long time, I mean really very long time. The first paper which kind of introduced mixture of experts was actually in the 1990s. So here you see this paper was published in Neural Computation in 1991, and the name of this paper was Adaptive Mixtures of Local Experts. One of the authors was Geoffrey Hinton, who is of course the pioneer in several machine learning domains, including backpropagation. So the idea of mixture of experts, it's not very new, and even mixture of experts was implemented in other language model architectures before DeepSeek did it. DeepSeek built upon that innovation and added some new tricks and techniques of their own. This is what I believe DeepSeek did so nicely. Instead of reinventing the wheel, they just borrowed what everyone has done and built on top of that, built something really cool and innovative. So this paper which I showed you, adaptive mixtures of local experts, this did not necessarily concern with language modeling, right? They did not introduce mixture of local experts for language modeling. They used it for a different task. They used it for supervised learning, and they showed that using mixture of experts, we could do some very new things with supervised learning algorithms. And then it was slowly brought into the domain of language modeling through Mistral, and later through many other players. Ultimately, DeepSeek used all of that knowledge and built something powerful on top of that. So here I just wanted to give you a context of mixture of experts, its history, and why I'm calling it a DeepSeek innovation. So although I'm calling it a DeepSeek innovation, please note that they were not the first to come up with the name itself, to come up with the idea of mixture of experts. All right. So in this lecture, I'm going to give you just an introduction and a visual feel of what this whole idea of mixture experts is. So as I've written here, another innovation made by DeepSeek is a very creative usage of a technique called mixture of experts. Okay. So first, let's start understanding how mixture of experts is used in language modeling. In these series of lectures, since they are very focused on LLMs, I'm not going to give you a historical context of mixture of experts because there is a whole literature on that. I'm directly going to start with language modeling. So if you look at the transformer block looks something like this. We have an input. So let me play this GIF once for your understanding. We have an input block where we have tokenization, token embeddings, positional embeddings. We have the transformer block where all the magic really happens. Here we have the layer normalization, multi-head attention, dropout, another layer normalization, feed forward neural network, dropout, and then we have an output layer where the input embeddings are converted into the logits matrix and then we predict the next token. Mixture of experts is an innovation which is especially concerned with one block among this entire architecture, and that's this feed forward neural network. So, if you carefully look at this feed forward neural network, it kind of looks something like this, where if this is the input embedding dimension, it projects it. The feed forward neural network projects the input embedding dimension into a hidden layer whose dimension is four times the embedding dimension, and then it projects it back into the original input dimension. So I like to call this neural network the expansion contraction neural network. Here there is an expansion when we go from the initial layer to the hidden layer, and then finally there is a contraction from the hidden layer back to the original dimension. So when we use a neural network like this, it retains the original dimension, but the input embedding goes into an expansion and a contraction. The reason we use a feed forward neural network here is because it allows the language model to explore a much richer space. It increases the dimensions, the number of dimensions by a huge amount. So it is one of the critical components of the transformer architecture. And experiments have shown that if this component is removed, the language models don't perform as well. So the feed forward neural network is one of the key components of the language modeling architecture. But one thing to note is the number of parameters which the feed forward neural network actually takes, right? So let us try to estimate this. If you have a transformer block, one transformer block, let's say, and the input embedding dimension is 768. So how many parameters will be there in one such feed forward neural network? So 768 in the, let's see, in the expansion layer, we have 768 in inputs and 4 into 768 hidden layer dimension. So the number of weights will be 768 into 4 multiplied by 768. Those are the number of parameters in the expansion layer, and the number of parameters in the contraction layer are similar. So the number of parameters in the contraction layer are again 768 multiplied by 4 times 768. Correct? So if you do this calculation, let's do this. So 768 multiplied by 4 times 768, that's going to be equal to this. And if I multiply this by 2, that's going to be equal to this. So this is actually equal to 4 million, right? And if you multiply this by 12, so if the number of transformer blocks are 12, that is around 56 million parameters. So this is for one transformer block, and that's around 4 million parameters. So if you have 12 such transformer blocks, you get around 48 to 50 million parameters which are present in the feed forward neural network. The reason I'm showing this to you is because the feed forward neural network has a lot of parameters. And what this does is that this affects the training time of the language model as a whole. This increases the training time of the language model, and it also increases the inference time of the language model. Mixture of experts optimizes this by reducing the pre-training time, and it also actually reduces the inference time. And now let's see how mixture of experts does this. So first, what I've written here is that We call this neural network the compression expansion or the expansion contraction neural network. What mixture of experts does is that we have multiple such neural networks which are called as experts, which are present in the transformer block. So instead of having only one neural network over here, we have multiple neural networks. In this figure, what I've shown here is that there are four such neural networks, and each neural network which is now present in the transformer block, it is called as an expert. So remember here I'm showing with respect to one such transformer block, right? In one transformer block, instead of having just one neural network, we now have one, two, three, and four neural networks which are present. And such four neural networks are present in all the transformer blocks. If you have 12 transformer blocks, we have four neural networks in all the 12 transformer blocks. Each neural network here is called as an expert. Now you might be thinking, what is the main advantage of this, right? Because it seems that we are adding more things. So how does it really help with respect to the pre-training and the inference time? So the main reason or what these experts actually do is that what's the need to add multiple experts? So adding these experts actually allows the model to be pre-trained with far less compute as compared to a dense model which is without experts. And adding such multiple experts also allows for a much faster inference as compared to a dense model without experts. Why is this possible? How come adding more neural networks reduces the pre-training compute time and also the inference compute time? Again, let me go through what's written here. Adding multiple experts allows my pre-training to be done with far less compute, and adding multiple expert allows my inference also to be done much faster. How is this done? So the main hint is that you have this word here, right? And that covers everything, that's dense. If you don't have a mixture of experts, then the neural network is dense, meaning all the parameters, all the weights are completely activated here, right? Nothing is set to zero. But the whole idea of mixture of experts is something which is called as sparsity. So in a dense model, every input token passes through all the parameters, that is all layers and neurons. So whichever input token which I have here, it passes through all of these parameters, all 4 million parameters in each transformer block. Every input token passes through all these parameters, so I have to do all those computations. But in a mixture of experts, only a small subset of these are activated for any given input. So if there are 64 experts, I'll have only two of these experts activated at one time. And if you have 64, you can even make sure that the dimensions of each are smaller. So if the dimensions of each 64 experts are smaller than 768, and I have only two experts which are activated for every token, that will reduce my amount of computations by a huge amount, right? Because now, if I have 64 such experts, and if the size of each is, let's say, 128, the dimension, and I have only two such experts which are activated, so that's 128 into 2, which is 256. This is three times smaller than 768. So the whole idea is this idea of sparsity. The whole idea is that of sparsity, which means that whenever I encounter a new token, it will not be passed through all of these experts. It will be handled by only a subset of these experts, and that is decided by something called sparsity factor. Here I have shown only four experts, right? But actual models have maybe around 64 experts. So if you have 64, every token will only be passed to two of them. Let's say all others will be inactive during that time. What this does is that every expert is specialized in some sort of computation. And now let's say one token is passed, I don't need to activate all the other tokens, all the other experts. I only activate those experts which are specialized for that particular computation based on the token which is given. So I reduce my pre-training time, I reduce my inference time as well by this trick of the sparsity. So this, if you can see this particular figure, this illustrates the idea of sparsity. This figure and some other figures which I am going to show you now are taken from this blog by Martin Grothendorf. This is one of the best blog for understanding mixture of experts. I'll also attach the link to this in the comments. So this is a figure borrowed from that blog, and here you can clearly see that, let's say these are my input tokens, right? And I'm looking at one transformer block where there are four tokens. What I'm showing here is that, let's say I'm looking at this particular token for now. You see that expert 1, expert 2, and expert 3 are not activated for this particular token. Only expert 4 is activated. This means that there is a sparsity factor of 1 by 4, which is 0.25. So for every token in this input sequence, it will be routed to only one of the four experts. And then we get the output. That reduces my pre-training or the inference time. So this whole idea of sparsity and mixture of experts was not novel. It was introduced in 1992 paper, actually 1991 paper, which I showed you at the start of this lecture. But they used it for a very new task. What they showed was that they used this idea of mixture of experts for the task of vowel discrimination. So they used this vowel discrimination task, and they showed that this can be achieved not by one neural network but by multiple neural networks, and by selecting the neural networks in a sparse manner. So they have a figure here, you see. This is a really important figure because what we are going to see eventually in the mathematics of mixture of experts is the same thing. So we have borrowed this concept, which was innovated around 30 to 35 years back, which again highlights the power of doing research and how research accumulates across multiple years and helps us. So we really stand on the shoulder of giants, right? So they have used mixture of experts for vowel recognition and for vowel identification, and they have clearly seen that based on the particular vowel, one of the multiple experts is actually activated. So they show that based on the input, there is a specific expert which is routed to that input. All the experts are not used for every input, and which is the whole idea of sparsity. And they tested it with 4 experts, 8 experts, etc. And if you take a look at the abstract, let's read out the abstract. We present a new supervised learning procedure for systems composed of many separate networks, each of which learns to handle a subset of the complete set of training cases, which means that each expert is specialized in some sort of a task. It therefore, we demonstrate that the learning procedure divides up a vowel discrimination task into appropriate subtasks, each of which can be solved by a very simple expert network. So let's say if you have a task which is a complex task, it is divided into subtasks, and each of these subtasks is performed by a separate neural network, right? So not, we don't need a one giant network. It's split into multiple smaller networks, and each of these expert networks does a specific task. um, there is a thing called a selector or a gating network, which basically selects which expert to use for the given token. We'll come to the mathematics later. For now, just remember that for every token, we don't have all the experts which are activated, but only a selected set of experts, which is the whole idea of sparsity. Out of this lecture, if there is one takeaway you should have, is the concept of sparsity. Um, All right. Now, what I want to show you is that I want to show you what do these experts really learn. So I've been telling you that the experts specialize in certain type of tasks, right? So you might be curious for a language modeling, uh, example. What do these experts really learn? So if you take a look at this paper, this is called STMOE, designing stable and transferable sparse expert models, and this was published in 2022. It's one of the most famous mixture of experts paper. And if you scroll down below, if you reach towards the end, here they have a table number 13 where they actually show what the different experts are learning. So here the layer corresponds to the transformer block. So if you look at layer number 2, you see that the experts in this layer are learning the punctuation. So whenever there is a punctuation in the input sequence, that is routed to these particular experts who are trained to understand punctuation. So this column is routed tokens, which means that whenever we have a punctuation, it will be routed to these experts in layer 2. Similarly, if you look at conjunctions and articles, the and, if, etc., that's routed to experts in layer number 3 and let's say layer number 6. If there are verbs such as falling, identified, struggling, falling, signed, designed, disagree, they are routed to layer number 1. If there are visual descriptions like color, spatial position, like blue, inner, over, open, dark, blue, upper, those are directed towards specialized experts in layer number 0. If there are proper names like Mart, Colin, Ken, Sam, Angel, etc., those are directed towards specialized experts in layer number 1. If there are tokens which represent counting and numbers, right, like after, then 7, 25, 4, 54, those are diverted or routed to experts in layer number 1. So from this table, we can clearly see that experts specialize in punctuation, conjunction, articles, verbs, visual descriptions, proper names, counting, and numbers, which clearly shows that experts actually specialize in certain tasks, which means that out of these experts, which I'm showing on the board here right now, out of these experts, maybe this expert learns to deal with punctuations like comma, then semicolon, full stop, etc. Maybe this token or this expert learns to deal with verbs. Maybe this token learns to deal with numbers. So this expert learns to deal with numbers. Maybe this expert learns to deal with conjunctions, etc. So whenever token comes in, if the token is a punctuation, it will be routed to this expert because it's specialized. Whenever a token is a verb, it's routed to this expert because it's specialized. So now think about it, right? If you were using the earlier feed forward neural network, whichever token comes in, I'm activating all my 4 million parameters in each block, which might not be needed. If I know that one particular expert can process my punctuations, why do I need to activate all the other parameters? It makes sense for me to activate parameters of this much smaller specialized neural network. And due to this specialization, I only activate that expert and I don't activate other experts at all. That saves me a lot of pre-training time, and that also makes my inference a lot more faster. So actually, all the modern LLM architectures are now using mixture of experts. If you see Llama 4, which was recently released, uh, Llama 4 uses mixture of experts. So let's see whether MoE is mentioned. Yeah, Llama 4 is their first model built using mixture of experts architecture, and this model is the latest coming from Meta right now, which means that mixture of experts is almost one of the most modern and innovative techniques, which is used by DeepSeek, which is used by Llama also, and that's predominantly because this intelligent use of specialized experts, right, which are sparsely activated based on my input token, that saves my pre-training time, and that also makes my inference faster. Okay, so we have understood the mixture of experts intuition. What do these experts learn? I'll be sharing the description to this or link to this paper in the description below. The last thing which we are going to look at in today's lecture is that when we see mixture of experts, sometimes we just look at one transformer block, right? And we see that one of these experts or sparse combination of these experts is activated for a given token. But if you remember, our language model architecture has multiple such transformer blocks, and there are experts in each of this transformer block. So I just want to show you the journey which is traveled by an input sequence through multiple such transformer blocks, right? So let's say the input sequence is what is 1 plus 1 followed by a question mark. Okay, that's my input sequence right now. And let's say I'm focusing on this one right now as a token. So this token is converted into a token embedding, and it will be, if I'm looking at one transformer block, and if I have four neural networks or four experts, it will be routed to one of the experts. So if the sparsity factor is 1 by 4, all these other experts will not be utilized. It will be routed to this expert, which deals with numbers. So in this first transformer block, this one will be routed to this expert, and then we get some output. What I want to show here is that there are different such transformer blocks, right? There might be 12 transformer blocks, and there are multiple experts in each transformer block. So if this one is routed to a particular expert in the first block, it is completely possible that it's routed to a different expert in the second block, it will be routed to a different expert in the third block, and right till the 12th block, it will be routed to a different expert. So it does not necessarily mean that if one is routed to expert number one in the first transformer block, it will only be routed to expert number one in all the blocks. No, experts in different transformer blocks might be specialized on different tasks. So if expert 1 handles numbers in the first transformer block, expert 3 might handle numbers in the second transformer block. We do not encode this information a priori. That's learned based on the input sequences. So actually, this illustration explains it all. If you look at this input sequence, right, and if you look at this particular token, it might go to expert number one in the first layer or in the first transformer block, expert number three in the second block, expert number two in the third block, expert number one in the fourth block, etc. And then finally, I get my next token, which is MoE. Now, when the next token is passed in, let's look at this next token now. It might go to expert number two in the first block, expert number two in the second block, expert number two in the third block, and expert number three in the fourth block. And then after I come out of my feed forward neural network, I go through the rest of my LLM architecture, the logits matrix, then I get my next token prediction. And if I look at this next token next, it goes through all my transformer blocks, right? Goes to third expert first, second expert, third expert, and then again the output from here goes through. The output from here goes through the rest of this rest of this LLM architecture. I have my logits matrix, and I have my next token prediction. So this leads to my next token prediction task. Uh, for my this input token. So the point of this illustration is that when you think of mixture of experts, normally people just think of this one neural network replaced with multiple neural networks, right? But this replacement happens across all the transformer blocks. So I have multiple neural networks not just in one transformer blocks but in all transformer blocks. So that visualization is very important for you to keep in mind. All right. One last thing before I end the lecture is I want to show you how DeepSeek uh, implemented a mixture of experts through which papers. So they had this paper called DeepSeek MoE, which was released on 11 Jan 2024, which is the paper which shows the mixture of experts architecture. So they started with base or vanilla mixture of experts, and they then implemented a lot of new things such as fine-grained expert segmentation, shared expert isolation, then load free. They also have, so version 2 did not have a load free loss balancing. So version 2, which came in June 2024, used this mixture of experts architecture, which was released in Jan 2024. And version 3, which came in Jan or Feb 2025, that further modified the mixture of experts because they use something called load free. They use something called loss free load balancing. So they used the fine grained segmentation which we saw earlier. This, if you see, so the main innovations in the mixture of experts which DeepSeek introduced is fine grained expert segmentation and shared expert isolation. So in V3, which is the latest, which was the latest model released in 2025 and which became so famous, they definitely used fine grained segmentation and shared experts, but they also used something called loss free load balancing. We are going to see all of this eventually, but first it is very important for us to understand the mathematics behind mixture of experts. So in the next couple of lectures, what we are going to see is that we are going to next dive deep into the mathematics of how mixture of experts actually operate. So we are going to see traditional mixture of experts first. Then we are going to see the innovations which DeepSeek introduced, such as fine-grained expert segmentation. We are going to see what shared expert isolation means, and then we are also going to see how what loss-free load balancing is. So this is the whole plan for understanding mixture of experts. It's one of the most modern concepts in language model architecture, and it has become very famous recently. So it's very important that all of you understand the introduction and intuition. But as always in these lectures, I don't stop at the intuition, but I'll go through the entire matrix multiplication calculations in a lot of detail. So if you see, I'm just scrolling down below at the set of lecture notes which I have planned for mixture of experts. It's a pretty expansive topic, so I want to cover the mathematics in detail, and I want to show you everything of how mixture of experts work from scratch. So stay tuned for the next lecture, but please make notes along with me. This is a very important topic. Once you understand this, you will understand the MLA, latent attention, which you covered before, and mixture of experts, which are the two cornerstones on which the DeepSeek architecture rests. Thanks everyone, and I look forward to seeing you in the next lecture.